Hello everybody and welcome to today's lesson on using proportionality theorems. Today our objective is we will be able to use proportionality theorems with triangles and parallel lines and calculate segment lengths. Now let's first remember how we prove that two triangles are similar. And similarly to the last class, this introduction is not on your notes, so just lean back and watch. Are these two triangles similar, and how can we know that? First, you see that they are again overlapping, so I'm gonna draw them out separately. We have two triangles. We have triangle QSR, which is the larger one, and QSR has side lengths that are given here, which are 7, and the lower one is 3 plus 7.5, in other words 10.5. And then we have the smaller triangle TUR, and that has side lengths 5 and 7.5. So how can we show that these two triangles are similar? We have three postulates or theorems that we can potentially use to prove the triangles similar. The angle similarity postulate, the side similarity theorem, and the side similarity theorem. We are given two sides for each of the triangles, so let's calculate if these sides are proportional. Looking at the two upper sides, we have 7/5. That doesn't reduce any further. And at the two lower sides, 10.5 divided by 7.5. Now that may be able to be reduced. Let's use our calculator to find this out. We can put 10.5 divided by 7.5, and then let's look at that answer and convert it back into a fraction, math 1, and we get 7/5. And these two ratios are indeed the same. So we have two pairs of corresponding sides that are proportional. Unfortunately, we don't have a third side given, so we won't be able to use the side similarity theorem. But let's see, do we have any angles? Looking back at our picture, at our original picture, we see that angle R is right here, and that angle is an angle that belongs to both triangles. This is actually the same angle for triangle QSR as it is for triangle TUR. So angle R is congruent to itself, and that is because of the reflexive property. So indeed, we can use SAS because this angle is also nicely included between the two given sides. SAS can prove that these two triangles are similar. Could we have also figured it out another way? Yes, actually we could have. Because let's look at these parallel marks we have here. So apparently segment SQ and segment TU are parallel, and they are being crossed by two transversals. So we have corresponding angles here, and we have another pair of corresponding angles here. Let me mark those down at the triangles that we drew ourselves. Angle Q is corresponding to angle T. We don't even need the third angle pair S and U because of our angle similarity postulate and our third angles postulate we can use this to also prove that the triangles are similar. But let's spend a minute and look at our original picture that had the two triangles overlapping and the two parallel segments. Here that creates a whole bunch of different segments with the lengths given. So let's spend a minute and look at how these segments relate to each other. For example, segment QT that has a length of 2. How does that relate to segment SU with a length of 3? We can create a ratio to show how they are related, and that ratio would be 2/3. And then we have the sides next to them, TR, which is 5, and UR, which is 7.5. So 5/7.5 is another ratio, and that's a ratio that can actually be reduced. And what we get when we do that, we will get 2.3. We can do this again on the calculator, just like I showed you a minute ago. So the ratios between these two corresponding segments are apparently the same. Now we could also relate segments in different ways. We could also relate the segment 2 to the segment 5 and write 2/5 as a ratio, and then relate segment 3 to segment 7.5, and 3/7.5 can be reduced, and again will give us a ratio of 2/5. Now I want you to realize that these two ratios are not the same as our scale factor that we add up here, 7/5, with the scale factor of the two triangles. We have different and new ratios, but they stay the same for corresponding parts as we relate them to each other. So let's go ahead and write this down, because there's a theorem, the triangle proportionality theorem, that is the basis of what we just found out. And here's how it goes. The triangle proportionality theorem states that if a line is parallel to one side of a triangle and intersecting the other two sides, let me mark these things, parallel to one side of a triangle and intersecting the other two sides, then it divides those sides proportionally. What do we mean by that? Let's look at the example given here on the right. We have segment QT, and if we relate segment QT to segment SU, that is going to be the same as relating segment TR to segment UR. And please note and be careful that we always have to go in the same order for ratios and for proportions. You know that. This time we went from the top to the bottom, QT related to SU and TR related to UR. But we can go different directions also, as long as we do it consistently. We can also relate segment QT to segment TR and going from left to right, and the ratio of segment QT over segment TR has to be equal to the ratio of segment SU related to segment UR. There's also a converse of the triangle proportionality theorem, and just like converses always, they flip the order of the two parts of a statement. And the converse of the triangle proportionality theorem states, if the sides of a triangle are divided proportionally, then the line dividing them will be parallel to the third side of that triangle. Again, the converse flips the two parts of the statement around. This time we don't know that the line dividing the segments is parallel. We need to find it out given the length of the segments that are created. Let's look at a couple of examples. Number one, in the diagram, AB is parallel to CD. We have that marked here nicely. AB is parallel to CD, and we're given some lengths of the segments. BD has a length of 15, AC has a length of 10, and CE has a length of 18. We are supposed to find DE. We don't know what DE is yet, so I'm going to put X as a variable here for the length of segment DE. Now let's go and set up a proportion. We can do that different ways. We can relate 15 to 10. So 15 over 10 has to be equal to X over 18. And then we go ahead and solve that proportion. We could have set up our proportion a number of different ways. For example, we could also have related 15 to X, and that would have had to be equal to 10 to 18. We can do a couple of different things, but we always have to follow the same logic as we set up our proportion. We chose to use 15 over 10 is equal to X over 18. Now before we go ahead and solve this proportion, let's actually simplify our fraction on the left. 15 over 10 can be simplified into 3 halves. And now let's multiply it all out. 2x is equal to 3 times 18, which is 54. Let's divide both sides by 2. We get x is equal to 27. And since we were supposed to find DE, let's write DE is equal to 27. So example number 2 is something where we need the converse of the triangle proportionality theorem to find our answer. In the diagram, PQ divides side LN and MN into the lengths shown. Determine if PQ is parallel to LM. So let's choose our segments and set up our ratios and proportions. What about taking LP and relating that to MQ? So LP over MQ, or in other words 18 over 27, now has to be the same as PN over QN, in other words 16 over 24. Now we can go ahead and cross multiply right away. Alternatively, we can check if we can simplify these fractions. 18 and 27 can be divided by 9, and we get 2/3. 16 and 24 can both be divided by 8, and we also get 2/3. So that checks out. Now again, we could have just gone ahead and cross multiplied. We should also get the same answer in terms of are they equal. Let's cross multiply, and you're welcome to use your calculator for that. 18 times 24 has to be equal to 27 times 16. 432 is equal to 432. So yes, that's indeed the case. And we can say, yes, segment PQ is indeed parallel to segment LM. Very good so far. Go ahead and watch the second part of the tutorial where we will discuss 2 more proportionality theorems.